So today's speaker is Thomas Queller from Amsterdam on CFTs with supergroup symmetry.
Yeah, so thank you for the invitation to be here and to be able to give this talk. Today I will talk about two-dimensional conformal field theories with supergroup symmetry, and another alternative title could be from supergeometry to logarithmic conformal field theory. This is joint work I did in the last year with Gerhard Götz and Volker Schomerus, and also with Thomas Kreuzig and Volker Schomerus. Let me sketch why these theories with supersymmetry are important. So first of all, there are plenty of examples in string theory, and I probably don't need to mention that supersymmetry in the target space is desired because you want to have stability. So usually supersymmetry guarantees a stable vacuum without tachyons. It's useful to prove finiteness theorems, and sometimes you would like to have it for phenomenological reasons. Then, of course, and probably that's the reason why most of us are here, there are these ADS spaces, maximally supersymmetric solutions to supergravity, which play a very prominent role in the ADS-CFT correspondence. And then finally, we also need to discuss these theories which have target space supersymmetry in the context of the pure spinor formalism, which provides the most promising way of quantizing flux backgrounds, and in particular backgrounds which have Raman-Raman flux.
Why did you say this?
Why? What do you mean?
What do you mean by this sentence?
That it's the most promising way?
Yeah, I mean there's so far no simple zero information.
I mean, at least from the conceptual point of view, it doesn't have the problem that the Raman-Levé-Schwarz formalism has, and it doesn't have the problems that the Green-Schwarz formalism has. So from that conceptual point of view, it's probably the most promising way. Maybe not from the calculational one at the moment, but I hope this will add to this topic. So.
Well, BRSD operators are nice, right? BRSD operators are nice.
Yeah, but I mean, in terms of as a practical person who wants to compute the spectrum, I don't think it has produced any results.
That's fine, but
that's why
if you want to do more than compute the spectrum, if you want to know about BRSD cohomology and stuff like that, which has many applications.
I don't.
Shouldn't the BRST cohomology tell you the spectrum?
Sure.
Very information.
No, I mean,
I don't think they've got that right.
that's true, but
Anyway.
it's nice that they have a BRSD operator.
So please consider this to be one of the steps towards a solution in that framework. So here,
Just a question out of interest: is it in a simple way that the sigma models that you're talking about enter directly in the pure spinor formulation? Are these models directly relevant to that, or do you have to take them and kind of gauge them in some way, or add goes?
and in the framework that Kostas Skanderis was presenting here 2 weeks ago, I think, you would have a sigma model on the supermanifold, tensored with a sigma model on the pure spinor space, and then you would implement this whole pure spinor constraint business. So in that sense, it would really be a constituent which enters like this without any additional input.
But in particular, would you expect the solution of the sigma model without constraints, which is presumably what you're talking about here, does that have direct relevance to this pure spinor formalism? In other words, can you then impose constraints at the quantum level, as it were, and say something about
and that's
strings?
something we cannot do right now.
Right.
I mean, the variables you have in the sigma model here, they would enter this BRST operator that Berkowitz was considering. So, and he was formulating it in a flat space. So you would need to think a bit how that translates. I mean, you can always go to the Vielbein formalism and work formally with flat indices, and in that context you can do it probably, but then you lose all these nice features of having solutions to all orders in alpha prime. So yeah, I guess there's more work needed on that side, but that will not be the topic of my talk. So here you see these ADS spaces, or a whole bunch of ADS spaces, which all can be formulated as cosets of supergroups in one way or another. And if you pay attention to these three-dimensional ADS spaces, they can all be formulated directly as a supergroup. For instance, as PSU11/2 or D21 alpha. So in my talk, this will be an example of what I'm going to present.
What is alpha, by the way?
Alpha can be considered to parameterize the ratio of the radii of the three spheres. So
you got some references before that an ADS3 process 3 sometimes is also considered as a product of two processes, right?
you can also formulate it as PSU11/2 times PSU11/2 over SU2 times SU2
Yeah,
or so.
isn't that what people often say?
That was what Berkowitz was proposing, but yeah, let me just skip over it. I won't talk about this anyway. Okay, so the usual way of letting strings propagate on a supermanifold or on an ordinary manifold is to consider two-dimensional sigma models. So you would study maps from the two-dimensional worldsheet, a cylinder in this case, to the target space. So you consider embeddings of this two-dimensional worldsheet. In this case, the coordinates that you have on the target space are promoted to fields, which depend on the worldsheet variables. And if you have isometries on M, they will act on these fields. So that's the kinematical picture. If you want to study the propagation, you need to specify the dynamics. So you need to specify an action functional which depends on these fields or on these coordinates. Then obviously the target space usually has some additional parameters like symmetric or gauge fields, fluxes, the dilaton, and all these enter into the dynamics. The supersymmetry of the model would mean that this action is invariant under the action of the isometries, and the conformal invariance means that the fields, the background field solves the supergravity equations. Oops. So what I will do here is just the first step, namely solving a quantum nonlinear sigma model to all orders in alpha prime. And then in the second step, one would have to impose some constraints in order to end up with a physical string. But that's something I'm not going to talk about. So here's a second class of models which have supersymmetry, and they arise in condensed matter theory. So for instance, you can consider disordered systems, and by a trick invented by Efetov, you can map these disordered systems to supersymmetric nonlinear sigma models. Models where it applies to are the spin quantum Hall effect, for instance, the integer quantum Hall effect, or more independently, polymer physics and percolation. So let me add some technical observations. Unfortunately, if you consider these cosets, then the standard constructions that you have available in conformal field theory, they don't apply in many cases. For instance, the chiral algebra is rather unknown in many cases, or it is very small where it is known. For instance, for the ADS3 background with Ramond-Ramond flux, it's known to be rather small. Then it turns out that if you have target space supersymmetry, you end up with logarithmic conformal field theories. So that's what my talk will be about. And that has first been recognized by Rosansky and Saleur in the beginning of the 90s. And then there's a whole bunch of papers which culminated basically in what I present here. Sometimes these models also have new kinds of moduli. For instance, in ADS3, you can have mixtures of Ramond and Lewis-Schwarz fluxes. So the plan of my talk is the following. I would like you to understand why logarithmic conformal field theories arise in this context. And to do that, I will first of all tell you what the specific features of two-dimensional logarithmic conformal field theories are. And then I would like to discuss a specific class of these models, namely type 1 supergroup Westoomino-Witten models. And I will start with a discussion of this GL11 Westoomino-Witten model, which can be considered to be a supersymmetric version of two-dimensional Minkowski space. And then it will also apply to this model the supersymmetric version of ADS3 times S3, but just with Lewis-Schwarz flux. And then later I will also comment a bit on other ADS backgrounds, if I have time. Okay, so two-dimensional conformal field theories in a nutshell. If you have a two-dimensional conformal field theory, you always have a chiral algebra, which factorizes into left-moving holomorphic degrees of freedom and right-moving anti-holomorphic degrees of freedom. And you always have an energy momentum tensor in both of these copies. So if you have a free boson, you can take the derivatives of the free boson and they would generate an Heisenberg algebra. So that's familiar to everybody. Then you have fields or vertex operators which can be considered as representations of your chiral algebra. In the free boson case, you can act with your currents on the vertex operator, and it gives you, in this case, the charge of the vertex operator. So all these vertex operators carry a representation label, in this case, a charge. And you can organize these fields in a space of states, which is a direct sum over representations of your chiral algebra. In the case of the free boson, it would just be an integral over all the momenta that you have. And later on, we will also find more complicated state spaces. So that was for ordinary CFTs. For logarithmic conformal field theories, you typically have operator product expansions which look like this. So you would have a term which you expect, which has just a power law behavior, and then you also have an additional term where you have a logarithm appearing. And if you think a bit about this operator product expansion, it turns out only to be consistent with scaling if L0 and L0 bar are not diagonalizable. In this case, it would mean that L0 applied to little omega would lead to capital omega, and L0 applied to omega would be 0. So omega would be sort of the vacuum, but it has a logarithmic partner, namely little omega. So this automatically implies that the theory is non-unitary because you don't work with irreducible representations. And there are also issues with factorizations. For instance, you have to impose that rotations are diagonalizable, but the dilatation operator L0 plus L0 bar is not diagonalizable. And since L0 and L0 bar act on left moving and right moving degrees of freedom and are sort of independent, it's important to find out how this can happen. So the insight is that certain representations of this chiral algebra cannot be chiral. So they cannot be written as a tensor product, because then L0 and L0 bar would really act independently, and you would never have the chance that the difference is identical to 0. So you have to have representations which don't factorize in this form. But then the big question is, which representations should you take? And for the logarithmic triplet model, that has been solved by a brute force calculation in the mid-90s by Gabadil and Kausch. For the supergroup Westermino-Witten models that I will be talking about, it naturally comes out of the supergeometry underlying the model. And recently there has also been a general proposal where D-branes are used to impose constraints on how the state space can look like, and that was done by Gabadil and Runkel. And I should also say that the results of these two calculations seem to be consistent, and so that makes hope for the future that this is indeed the correct proposal.
Did you say on the previous slide that the dilatation operator in these conformal field theories is not diagonalizable?
Yeah.
So what's the consequence of that in terms of the spectrum of operator dimensions? I mean, you define a spectrum of operator dimensions, or?
Yes, you always have, you have always an operator which has a proper conformal dimension, and then you have a logarithmic partner which maps to this one which has a proper conformal dimension under
the
the
logarithmic
action.
ones don't.
Yeah, so you can always define it, the conformal dimension, but not every state in a multiplet has to be diagonalizable itself. But it's always connected to one state which is diagonalizable. So in that sense, you can define it. Okay. So now I will only talk about supergroups, and I will try to explain how these logarithms arise. So you should think about supergroups as being exponentiated versions of Lie superalgebras. And in order to make sense out of this statement, I will have to introduce what Lie superalgebras are. Then I will explain the representation theory and the subtleties that lead to this possibility of having non-chiral representations. I will derive how all this comes about in the harmonic analysis on supergroups, and I will explain how it is related to Westermino-Witten models. And I will first do that for a very cute example of GL11, and then later I will also talk about more general supergroups. So a Lie superalgebra is basically a Lie algebra with bosonic and fermionic generators. So it means that you take the definition of a Lie algebra, you impose that it has a Z2 grading, which decomposes it into bosons and fermions, and then you demand the usual relations like antisymmetry, but here you have to add some signs, and Jacobi identity, but again up to some signs because of the fermions. And the grading should be respected, so that means that a boson and a fermion commute into a fermion. So here in this talk, I will only be specific about supergroups of type 1, and that means, first of all, that they have a non-degenerate invariant bilinear form, which I need in order to specify the Lagrangian and to make sense out of the model. And then I also need a particular Z grading. So in this case of type 1, it means that the fermions, which sit in the grade 1, can be split into 2 bits, which sit in degree 1 and -1. But you don't have any additional terms. So all the bosons keep on sitting in the 0 degree here. Examples are GLMN, SLMN, or PSLNN, and you can think about these as block diagonal matrices, or not block diagonal, but block matrices which have bosonic blocks on the diagonal and fermionic blocks off diagonal. And I should also say you shouldn't think about Grassmann variables in this context. That's all with real numbers. I mean, if I say fermionic, then it refers to the commutation relations, but it doesn't refer to any Grassmann variables also. So in this grading, which I introduced here, is also useful in order to introduce a Gauss-like decomposition for supergroup elements. Namely, I can parameterize an arbitrary supergroup element in this form, where I put a factor to the left, which only depends on fermions living in this degree 1. Then I have an ordinary bosonic group element, which lives in degree 0. And then I have another element which includes fermions f-1 living in g-1. And these thetas here, this theta and this theta bar, they are now Grassmann variables. So you only need the Grassmann variables to define the group, but not the Lie superalgebra. Okay, so as I said before, we want to discuss nonlinear sigma models, and we would like to use the symmetry that these models have. If you have a supergroup, then it has a bunch of isometries, and these isometries are the supersymmetries of our model. In this case, you have a left regular action multiplying elements from the left, and you have a right regular action multiplying elements from the right. So that gives you a supersymmetry G times G. Usually it's not convenient to discuss symmetry on the level of this nonlinear space, G, but you would like to do it on a linear space. And you can do it on the algebra of functions f of G, and you just have an induced action where the group elements act on the arguments of the function. So a few remarks. If you consider the infinitesimal version of this, then you can realize it in terms of differential operators. These are just killing vectors, if you like. And these form also this Lie superalgebra. These differential operators can also be used to define the Laplacian, and the Laplacian is just the quadratic Casimir of this Lie superalgebra up to some normalization. Oops. So now I will be more specific about Wess-Zumino-Witten models, which are a particular class of sigma models. So you have 2 terms contributing to the action. First of all, a kinetic term, and then a topological term, which is a B-field term. And it turns out that this action is invariant under these transformations. So if you multiply an element from the left with some holomorphic function and from the right with some anti-holomorphic function, the action is invariant. And algebraically, so on an infinitesimal level, it leads to 2 copies of an affine Lie superalgebra. So you have A plus A bar is equal to G hat plus G hat, where G hat is, you can think about it as a Lie superalgebra where each index has an additional label n, which runs through all the integers.
Is the coefficient of the West, do you need the Wess-Zumino term
Yeah.
conformal invariance in these models, or?
In most of the models, not in all of the models. If the killing form is vanishing, the terms, it could be neglected. But for models where the killing form is non-zero, you would have to keep both terms, and also they have to be adjusted such that
The coefficients.
their coefficient is identical in certain normalizations. Yeah. So for the free boson, I said that the vertex operators are just the exponentials, and here you can also consider matrix elements of the group element, normal ordered, and these would be the vertex operators. So the dictionary that I will use frequently in this talk, and which will be valid if we are at large volume, so if we scale the metric to infinity, that's this one. So in the Wess-Domino-Witten model, you have always a state space, and in the geometric picture, it would correspond to the algebra of functions. Then you have a chiral algebra, namely this J of Z, J bar of Z bar. They form a Kac-Moody algebra, and this, or the zero modes of this, corresponds to the left-right regular action of G plus G, so to the isometry of your space. And on the right-hand side, it's implemented by differential operators, and you can identify these with the zero modes of these currents.
What's the nature of the matching between the relationship between the state space and the algebra
It's
of
not,
functions?
it's not a one-to-one matching, but you should think about, so if you forget about the ZZ bar dependence here, then you would just have a matrix element, and these matrix elements would form a basis of your algebra of functions. So you basically just consider zero modes. That's the idea. So it's not one-to-one, but it's from the CFT.
So it's really from the quantum mechanical reduction of the signal model to
Yeah.
respect to the
Yeah.
algebra of functions.
That's true. Yes, it's mini superspace.
Ah.
Yeah.
You mentioned you changed it and said that we now have a Kac-Moody algebra. So what sets the central charge?
The central charge is, you can apply the general formula for Wess-Domino-Witten models, which is C is equal to K times the super dimension of G over K plus the dual Coxeter number. So that's the central charge. You can just calculate it. Okay. So the question of the central charge was related to the dilatation operator or to the Virasoro algebra that you have. And the zero modes correspond to the Laplacian or Casimir operator on the geometric side. So if you use the Sugawara construction, you will immediately find that indeed the lowest order contribution is proportional to this Laplacian. The vertex operators are the eigenfunctions of the Laplacian, and the conformal dimension that you have in your CFT can be extracted from these eigenvalues. And there will be a small quantum renormalization, but in principle, this holds identically if you are at large volume.
If your group has rank more than one, then there will be higher arguments.
Yes, but usually they're not needed to describe the system. And usually you just work with the currents, and that's okay. That contains all the information.
What is it?
I mean, it would correspond to higher Laplacians, but usually people don't consider it because it doesn't contain more information than. And if you consider ordinary groups, then the Casimir, the quadratic Casimir, already specifies a representation uniquely, at least finite dimensional ones. And so you don't gain information by considering more Casimirs. Oops, oh, sorry. Okay, so let's talk about GL11. And in this case, you have very trivial commutation relations. You have two bosonic operators, N and E, where E is central, so commutes with everything, and N is a charge operator. And then you have two fermions, which have charge plus and minus 1 under N, and which have charge 0 under E, but they anti-commute into E. And then you can just use the usual trick and then exponentiate this Lie superalgebra in order to get this kind of decomposition. So you see here Fourier expansion in flat space, basically, flat Minkowski space, and then you have fermions sandwiched on the right and on the left.
The resulting action is quadratic in that case, or it's nonlinear?
It's an interacting model. It's
Isn't it?
nonlinear. Okay, so we all know this Lie superalgebra because it also appears in supersymmetric quantum mechanics. We just have to forget about the n operator. And if you're a mathematician, you also find a realization of it in the de Rham complex and Hodge theory. But maybe I shouldn't be explicit about this. So let's talk about representations.
You mean the supersymmetric harmonic oscillator?
That's supersymmetric quantum. I mean, maybe that's an example of supersymmetric quantum mechanics. So the typical representations, the standard representations, are Katz modules, and they are defined by these highest weight conditions. So we know that E and N commute, so we can choose it as a basis of our Cartan subalgebra, and we assume to have a highest weight state having eigenvalues E and N and being annihilated by psi plus. So that's the highest weight representation, and since psi minus is nilpotent, we can just act with it once, giving us a second state, and that would be this state labeled by n minus 1. So in these pictures, I will always draw the n quantum number horizontally. That will be a common feature of all these pictures. So then it turns out that if you have a Katz module where E is equal to 0, then it degenerates. And it exhibits a one-dimensional invariant subspace. So that means you can run into this state. You can go from the right to the left, but you cannot go from the left to the right because of the commutation relations. And then you have to distinguish Katz modules and anti-Katz modules. And in one you can run from the right to the left, and in the other one you can run from the left to the right, but not vice versa. So these
What does
would
the
be
action look like for this model, just in terms of the coordinates on the supergroup?
let me maybe, I will,
Only 4 of them. So.
yeah, no, it's very simple. Okay, let me write it. Oops. Okay, I'm not sure about the normalizations, but first of all, you would have a free boson, and then you would have another term which looks roughly like up to some factors here, or possibly signs, and then you have d theta bar, d theta bar. It's something like this, but I will.
Why is the thing that appears? That's
That's
appearing
an-
in the exponent there.
It's y. That's the
That's-
bosonic coordinate, one of the bosonic
It's
coordinates.
it's the free boson.
Yeah, that's one of the free bosons.
Right.
So you can think about this
So
as
that's the nonlinear term, the kind
Yes.
of kinetic term that couples to the boson.
yes, precisely. I will later present a more convenient way of writing this. Okay. So here's a summary on all kinds of irreducible modules you can have. Namely, I introduced this En, the Katz modules, and I also introduced this N, which always lives at E equal to 0, and these are one-dimensional irreducible representations. So the first ones, the two-dimensional ones, are called typical, while this other one is called atypical. It arises at a very specific point of parameter space for E equal to 0. You can think about E equal to 0 as being a BPS condition, if you prefer. So then it's important to know that these two-dimensional ones have a property of being projective. I won't explain what it means, but so these are, while the one-dimensional ones are not. And that means that the second ones are extendable because every representation has a projective cover. So a bigger representation, which is projective, and which includes this one-dimensional one as a sub-representation. And it's also important that these two-dimensional ones are not extendable. So if you see such a two-dimensional one, it always comes by itself. It never appears in a bigger representation. And a convenient way of dealing with these indecomposable representations and extendable representations is the concept of a composition series. So if I have such a degenerate Katz module, I can express it conveniently in this form, meaning that I have an invariant subspace corresponding to the representation n-1. And if I take the quotient with respect to this one, I will have another one-dimensional representation which is labeled by this one. Okay, so that's the composition series. It's just a way of encoding the graphical information here, if you like. The arrows, if you like.
Sorry, the last thing you were writing down is some short exact sequence with 0n in the middle.
I think it's not a short exact sequence. No, it's not exact. Not necessarily. In more complicated cases, at least not. So then you have more representations. I already mentioned the projective covers, and in the case of GL11, the projective covers are all four-dimensional. So you would have two states up here and down here, which in principle should lie here on the line, but in order to distinguish them, I drew them up here and down here. They have eigenvalue n. And then you have two further states which have eigenvalues n-1 and n+1. And the state on top here cannot reach by the action of any operator from the other states, but you can reach all the other states from this one. So that's the cyclic state. And down here you have an invariant subspace, a one-dimensional subrepresentation. The quadratic Casimir operator is not diagonalizable on this space. It would map the state up here to the state down here. And actually, in what I'm going to present later, this is precisely the reason why we can have a logarithmic conformal field theory. Because the non-diagonalizability of this Casimir will be related to the non-diagonalizability of the Laplace operator on the space of the algebra of functions. And that in turn will be related to the non-diagonalizability of the zero mode of the energy momentum tensor. So the occurrence of these representations will be the reason for the logarithms. It's also interesting to note that these projective covers arise as tensor products of typical modules if these E quantum numbers add up to 0. And that's partly a consequence of the fact that the tensor products of projective modules will give a projective module again. So these projective modules, although I didn't say what they are, they have a special property that they close under fusion or close under tensor products. And that makes it very convenient to have these representations in your CFT. Okay, here's a list of some invariant subspaces and quotients you can have in your theory for such a projective cover. I already talked about the one-dimensional invariant subspace. You can also have a two-dimensional invariant subspace corresponding to a degenerate Katz module. It turns out that these projective representations not only have a composition series where you use irreducible representations to write such expressions, but you can also use the Katz modules to write such composition series. And here in this context it means that you have two Katz modules, namely first of all this one here, up here, which corresponds to the first factor, and then the second one down here, which corresponds to the second factor. And if you take the quotient of this four-dimensional one with respect to this one, so if you just delete these two nodes, then you end up with this one, and that's precisely what I wrote here. So that's the way of reading these pictures.
So are all of these things representations, or they projective representations? I'm just getting a bit lost.
They are representations, and when I say projective, I don't mean projective in the sense of having some multiplier functions. I mean projective in the sense of category theory. So they're really honest.
The representations are the projective representations. So are the commutation relations satisfied up to a phase?
No. They are exactly satisfied. They are proper representations. As I said, the projective refers to category theory, not to this other notion of being projective. Yeah, I should have said that. Okay, apart from these Katz modules, you also find the dual Katz modules, obviously. You can also find three-dimensional subrepresentations Or if you prefer to mod out by this blue state, then you find another three-dimensional representation sitting up here. Okay, so these are the representations we have, or at least part of the representations we have. And now we would like to do harmonic analysis and see how the algebra of functions decomposes into these representations. So the algebra of functions has the following basis. You just take your favorite plane waves, so these ones, and then you have to multiply them with fermions. So that's the algebra of functions on the super group. And now I would like to organize these states according to their quantum numbers n and n bar. So I have a left moving action or a left action which has an operator n, and I have a right action which has an operator n bar, and these eigenfunctions have eigenvalues with respect to these, and I can draw that in a diagram like this. So I can forget about E and E bar because E and E bar are central, and I just fix it to a number and don't worry about it anymore. And then it turns out that these functions, they lie close to the diagonal. And these functions here, they are precisely on the diagonal for each value of n. And these functions as well, that's why I drew this line thick, because the fermions have opposite quantum numbers. So the quantum numbers of the fermions add up to 0. And then you have two off-diagonal contributions coming from these functions. They correspond to this line and this line. So that corresponds to a picture for all values of n, for all charges, for all momenta I can have. But since the fermions just at charge 1 or -1, I can also restrict myself to n being integers, or n being integers up to some fixed fractional value. So then I get this picture here. So I would like to organize these states into representations of my isometry, which is G plus G. And I start with a typical sector. So typical sector means E is not equal to 0. I have momentum in the x direction. And then if you consider the states with respect to the left action only, you get two-dimensional multiplets. So these green and the red lines correspond to two-dimensional multiplets. I get the same picture if I consider the states with respect to the right action. And I would like to know how it looks if I consider it with respect to the simultaneous action of both left and right. And not surprisingly, I just get these little boxes corresponding to tensor products of these two-dimensional Katz modules. Yeah? So that's the picture that's what you would expect for ordinary bosonic groups, and that's also what you find in these typical sectors. But unfortunately, these supergroups also have an atypical sector. And in the atypical sector, it turns out, if you do the calculation explicitly, that the states organize themselves into these projective covers, so into four-dimensional representations. And here I use the shorthand notation. So before that, I always had this diamond picture, and now I use this picture where I put two states on top in the middle and two other states at the borders of the line. So I have these pictures, and I have these pictures for the left action, and I have a similar picture for the right action. But now you see that the action cannot factorize anymore. I can, for instance, I can start, for instance, with the state, the circle state up here, and go down here, which would correspond to moving from up here to down here. Yeah? So I can move from up here to the side. Oops, oh no, I prefer to go to the left. So I can go here. And then I have two choices. I can either use the left action again to go to the state which sits below the middle state here, or I can use the right action to go from here to here. That's precisely the map from here to here to here. So these representations don't decouple anymore, and it turns out that this infinite number of states organizes itself in just one infinite dimensional representation. which is indecomposable. So it cannot be written as a sum of something simpler. And yeah, I should maybe add again that this has first been found by Volker and Hubert-Zalleur in a paper 2 years ago. And this will be the picture which is also valid for more complicated groups. And that's what I'm going to explain now. So I will introduce what we termed a free fermion resolution, which means rewriting the Lagrangian in a very nice way that you can actually solve the model. Then I will discuss symmetry and spectrum using, again, mini-superspace approximation. So that's the same ideas that I had before. Then I will be very brief on the quantum description, because basically you don't get any new information in this part. You just use that the isometries are lifted to an affine Lie superalgebra, and you just have to affinize everything, and then it all works out. And I will be a bit more explicit about how to calculate correlation functions. And
so basically, all you need to know is just Laplacian for this particle action. And then you study its spectrum. That's what you're saying.
Yeah, and then I get the truncations as usual. I get infinite dimensional extensions because I have an infinite dimensional symmetry. But basically, I just do harmonic analysis. Yeah. And let me repeat, the special features that all these models have are that the energy momentum tensor is not diagonalizable because you have these projective covers that leads to logarithmic correlation functions. You have non-chirality, so you have representations which do not factorize into a tensor product, and you have non-unitarity. That's a consequence of these two things. Okay, so let me start with the Gauss decomposition again. Let me remind you that this is ordered by the grading. So on the left I have this the +1 part, here I have the 0 part, here I have the -0 part. And if I plug this into the Polyakov-Wiegmann identity, then it turns out that I can rewrite it in a very convenient way. I get a Wess-Zumino-Witten model on the bosonic subgroup, which is slightly renormalized, which is not surprising. Then I have, if I include some additional fermionic fields, I can write the fermions in a very simple form. Namely, I have two free fermion actions, where the thetas are h equal to 0 fields and the p's are h equal to 1 fields. And I have an interaction term. And the interaction term is just this term here, where the p's are coupled to a vertex operator of the bosonic model. So what we achieved with this nice parametrization here is that we basically reduced the problem to a bosonic Wess-Zumino-Witten model. And this one is solvable or has been solved. And then we only need to include the effects of this interaction. So how to calculate with this? We will assume that the Wess-Zumino-Witten model for the bosonic subgroup is solved. The free fermion theory is solvable anyway. It's very simple. And then we treat this as a perturbation. So we will calculate correlation functions in the Wess-Zumino-Witten model by using correlation functions in the decoupled theory with an additional insertion of this interaction term. And what we still have to determine is what kind of fields can we insert in this correlator and how these fields map into the fields I have here in the decoupled theory. So that's what we would like to determine. And here we use what we already learned from GL11. We use the point particle limit, so we send the volume to infinity. We only keep 0 modes. We have to discuss the representation theory, and we do harmonic analysis.
So the perturbation you're adding, is it exactly marginal?
Yes, it's exactly marginal. I mean, it's not.
In principle, there's a dimensionless coupling associated with it.
No. Okay, I should be more precise. It has a very fixed value. It's not a marginal perturbation. You have to be at this particular point, and then it's conformal. You cannot perturb with it marginally. Sorry. Okay, so the interesting observation is that both Lagrangians, namely the decoupled ones, the decoupled one where you forget about the interaction, and also the other one, they have the same supersymmetry. So both have an affine Lie superalgebra symmetry, but it's realized differently. And in the interacting theory, the 0 modes of that precisely correspond to the isometries of the supergroup, while in the decoupled theory, you forget about informations, and then this G plus G is not directly related to the supergroup anymore. It's a different space. It's more like a flag manifold, if you like, but anyway. So the picture is the following. We have a supersymmetry, G plus G, and then we have the decoupled theory and the interacting theory, and in all of these, we have differential operators implementing the isometries. We have a Laplacian, which is just the Casimir of these ones. And then we have a representation space on which all this acts.
So the left-hand side is purely bosonic?
It's not purely bosonic, but
including the free fermions
it's
as well.
solvable. Yeah, it's free fermions, precisely. It's a bosonic model which is solvable plus free fermions. So the left-hand side is supposed to be simple, and what we would like to do is to construct a map, mapping things here on the left-hand side to the things on the right-hand side. And basically this map is induced by this interaction term. I won't construct the map explicitly, it can be found in our papers, but that's the idea, that the presence of the interaction term gives you a map from the left-hand side to the right-hand side.
Do you have to calculate all orders in the expansion of the exponential of the interaction term? Or does it truncate
No,
and so on?
since you have fermions,
There's a
it
selection rule.
truncates. Yeah, I should have mentioned this precisely. There's a selection rule and it truncates after a finite number of terms. The more fields you have, the higher it can go, but it's always finite. So let's solve the auxiliary problem for the decoupled theory. So the auxiliary algebra of functions is just the algebra of functions on the bosonic group tensored with these fermions, or with functions in the fermions. So that's the Grassmann algebra or exterior algebra. Then you solve the eigenvalue problem for the reduced Laplacian, for the decoupled Laplacian, and that's again harmonic analysis because the Laplacian is obtained as a Casimir operator of your symmetry generators. So all we need to know is how this F naught, this auxiliary space, decomposes with respect to the supersymmetry. Because once
So
we know...
lots of bosonic Westermann Witten models we're talking about in this context are generally non-compact here, or
they
what are the examples that crop up?
You can take GLMN, SLMN, PSLMN. They can be compact, non-compact, that doesn't matter. And for the Westermann-Witten models. Later, if you want to have Ramon-Ramon fluxes, you have to demand that the killing form is vanishing. But for this, it's enough to have any supergroup. You can also do that for type 2, which is technically a bit different, but in principle, you can do similar things. And I already mentioned that interaction term induces this action. So, and I won't be explicit how it looks like. So let's solve this. So let's decompose the representation space with respect to the isometries. If we, for the moment, just consider the bosonic action. So we just look how the space decomposes with respect to the bosonic symmetry. Then we can use the Peter-Weyl theorem in order to say that it's a direct sum over irreducible representations of this tensor product of a representation with its dual. Then the Grassmann algebra can also be analyzed in a similar way, and it turns out that these fermions theta and theta bar are independent. The reason is that they live in degree 1 and -1. And since each of these spaces, 1 and -1, forms a representation space by itself, we can factorize it into F times F star. So that's a certain representation, and that's its dual. And if you combine these two things, then obviously the bosonic representation content, or the representation content with respect to the bosonic subsymmetry is the sum over these products here. And now we have to analyze how these form super multiplets. So how these organize themselves into representations of the super algebra.
And presumably in many interesting cases, the bosonic submanifold is non-compact.
Yeah, for ADS3 times S3, for instance.
So then you'll have, in terms of your representation sum, you'll have both continuous
and discrete.
components. So
Yes.
what you wrote as a sum there, presumably,
Yeah, that is
you have to decide what you integrate over and what you sum over exactly.
Sure. If you have non-compact spaces, it would be a direct integral, and you have to, but still you can use the input you have from the bosonic side. I mean, for ADS3, you are right, you would have two contributions here. You would have an integral over the continuous series, and you would have an integral over the discrete series. But yeah, I mean, this is fairly general. That's what I meant with related knowledge, because Peter-Weyl theorem doesn't apply to non-compact groups so simply. Then you have to use Plancherel measures and such things. But in the spirit is the same. So now we would like to know how these tensor products form supermultiplets. And it turns out that they precisely correspond to these Katz modules that I already introduced before in the case of GL11. So, okay, I won't explain this in more detail. You can ask me later if you like to know about it. So it turns out that this auxiliary space of functions is just the sum over all the irreducible representations of these products of Katz modules. And the eigenvalues of the Laplacian can easily be determined. They are just the Casimirs evaluated on these representations. So we solved the problem on the auxiliary side now. Now we would like to map it to the interacting side. And in order to do so, we need to discuss some more representations. As I said, these Katz modules can be irreducible or typical, or they can be reducible but not fully reducible, and in that case they are called atypical. And again we have the correspondence of typical meaning non-BPS and atypical being related to BPS. So in order to write this more explicitly, I decomposed this algebra now into two terms, namely the sum over the typical representations and the sum over the atypical representations. These ones are, as I said, degenerate, so they have invariant subspaces, but nevertheless they occur in this decomposition. So then again we can discuss irreducible representations, which are obtained as quotients from these Katz modules, and we always have a projective cover of these irreducible ones. The projective cover coincides with the irreducible one in case of a typical module, but if it's atypical, it's bigger. It's really an extended representation. And what is important to note is that the trivial representation is always atypical. So the trivial representation is always sitting in here. So just to make sure you understand that these atypical sectors are really important. So they really exist.
The vacuum is supersymmetry invariant numbers.
Yes, and it's in here. Okay, so let's talk a bit more about these projective covers. It turns out that these projective covers have a Katz composition series, so you can give a list of Katz modules which sit inside of such a projective cover. And then you also find that there's a duality between these irreducible modules, Katz modules, and projective covers, which relates the number that the Katz module, or the number of times the Katz module appears in a certain projective cover, to the number of times an irreducible module appears in a Katz module. So you should think again about these pictures. So that's for GL11. Here you have a four-dimensional Katz projective cover, and it consists of two Katz modules, namely this one here with a red box and this one here. So it contains this one with multiplicity 1 and this one with multiplicity 1. So that corresponds to this bracket here. And then on the right-hand side you have the multiplicity of irreducible modules in the Katz module, and that corresponds to the multiplicity of these dots and one single dot in the Katz module. And if you look at it, it turns out that this relation holds, and it also holds more generally. That has been proven by these two mathematicians. So, and if one uses this duality, one can finally end up with this result, which is the decomposition result for the algebra of functions on the supergroup. So we see that in the typical part, we still have a sum over products of Katz modules. So nothing changed in the typical part. But in the atypical part, we again have to organize representations into blocks or into orbits, and then sum over infinite dimensional non-chiral representations. So somehow this map theta entangles these modules into something non-chiral. And these representations are responsible for the occurrence of the logarithms in this CFT. So it's interesting to restrict this to either the left action or the right action. And then it turns out that you find Katz modules and projective covers. And each of them comes either with a multiplicity of a Katz module or with a multiplicity of an irreducible representation. And here again, I mean, basically this formula is a realization of this duality, if you like.
Do you think it will also go the other way around, that if you have a logarithmic conformal field theory, that there's always somehow something in supersymmetry?
No, I don't think so. Okay, so I will be very brief about the quantum theory. So basically what we have to do is to promote the left-right regular action to a fine current superalgebra symmetry. Then we get a renormalization of the bosonic currents. That's pretty standard. And the currents closely resemble the differential operators. So there's nothing special here. Then the metric and Casimir eigenvalues are slightly renormalized, but you can forget about that in large volume. Energy operator is not diagonalizable because the Casimir has not been diagonalizable. You get a truncation of the spectrum related to the finite volume. You have affine representations because you have an affine symmetry, but they still factorize in the typical sector and don't factorize in the atypical sector. And then you might have to include twisted sectors if you have winding states, and spectrally float sectors if you are in non-compact spacetimes. But that's pretty straightforward. And as I said, correlation functions can be calculated algorithmically. So I just use this correspondence and do a perturbation series which truncates, and some of these functions will be logarithmic. So we also discussed d-branes, but in view of the time, maybe I just skip this and go to quotients. So you can do, in principle, a similar analysis for quotients of supergroups. And here I would like to talk about quotients where the action of H is just from the right. So I would have this identification. And again, we have a supersymmetry, which is realized geometrically by just multiplying the group element from the left. We don't have the right action here because it's gauged. Yeah? And then we have an algebra of functions again, which can be considered to be the algebra of functions of G, invariant under this right action. So, and on this space, we again have a left action of the supersymmetry. And you all know about this, so I won't be very explicit, but this identification here is not the one which leads to gauged Wess-Zumino-Witten models. And that's the reason why these cosets are very difficult to quantize. So that was just a very general statement about the geometry, but not all of these theories are conformally invariant. So when are these conformally invariant? It turns out that there's a huge class of models corresponding to generalized symmetric spaces, and they correspond to these ADSN times Sn spaces. And generalized symmetric space means that the subgroup H, which I divide out, corresponds to the fixed point set under an automorphism of G. If it's of order 2, then it would be a symmetric space, and if it's higher order, then it's a generalized symmetric space. And then there are several conformally invariant examples. I mean, for the ADS spaces, it has already been known a long time ago. But then there was a paper by Kagan and Young where they showed that if G has vanishing killing form, then this is automatically conformally invariant, at least to first order. And this includes ADS spaces, it includes flat superspace, and it includes superspheres. And in some sense, these generalized symmetric spaces also include these non-compact cosets where you take a complexified group and divide out the maximally compact subgroup. And this leads, for instance, to H3 plus or SL2C over SU2. And that has been pretty popular because it's the Euclidean ADS3 space, and it has first been introduced by Gawecki in roughly about the 90s. So for these models, you don't have any general algebraic construction. You don't even know what the chiral symmetry should be, how the chiral splitting should work. But recently there has been a proposal how these models, at least in the string theory picture, might be related to massive perturbations of gauge-Westermino-Witten models.
What does that mean? I mean, you still want them to be conformal. So.
In this case, you do some gauge fixing, and then you don't have conformal invariance anymore. So this is really just valid for the string theory, not for the conformal theory.
But these are not the same cosets, because the cosets you talk about are...
And you also discussed S2 and ADS spaces.
Yeah,
S2 would be an example of this right-handed right coset.
bosonic, yes, but not super. What I mean...
Yeah, but...
Okay.
Okay, we can discuss that later. Okay, so what I would like to stress is that all these features that I talked about, namely the presence of these logarithmic contributions, logarithmic correlation functions, they are also expected in these models. And I would like to mention the reason for this.
But you can only do this kind of analysis if you have a current algebra, right? These cases,
No.
In general, these cases are not expected to have.
I think you would still have the dictionary of mapping L0 to the Casimir operator.
That would somehow only tell you about the zero modes. Of the
Yeah.
problem. And
But
without
that
current
lifts-
algebra, you don't have the information to fill in the rest of the spectrum.
Sure.
Just the
I mean, I
zeros.
don't say I can solve the model. I just want to say that if I know that on the level of the zero modes, I get these not diagonalizable representations, then this will still be valid in the full CFT. Even if I don't, even if I cannot write the full CFT and cannot solve it, but this feature will certainly persist.
How can you be sure of that?
And I
Sounds
am
like you're truncating the model, then thinking about quantization in order to make that statement, right? It's not obvious.
I mean, the full model has to include the classical model in some sense if you send the parameters to infinity. So it has to include these not diagonalizable representations.
Or you mean they would somehow show up at least in the large radius then?
Yes, precisely. Okay, I don't make statements about the finite volume, but in the large volume limit you certainly get them. And then it's very reasonable to assume that you also get them for other values. Okay, but let me explain why I believe they appear. So if you think about this Peter-Weyl theorem that I showed you before, and if we now write this algebra of functions decomposed with respect to a left supersymmetry and the action of the right bosonic symmetry, then we get this formula. So we again get Katz modules with a certain multiplicity space here, and we get projective covers also with a certain multiplicity space here. And if H is bosonic, and that's important now, so H has to be bosonic, so it has to be a subgroup of this G naught, then gauging the right action only, it gives rise to these projective covers here, because we only need to decompose this space with respect to H. So we just get some multiplicities, but we keep the projective covers. That's important. And since we have projective covers, we have this logarithmic behavior. And this statement applies to all ADS spaces, at least in this Z4 formalism, in the generalized symmetric space formalism. It also applies to flat superspace, which is just the coset of super Poincaré over Lorentz. But it doesn't apply if we mod out by a supergroup. At least it doesn't necessarily apply.
You definitely have in mind these cosets which are used by Berkowitz. In the sense they are non-unitary. In that sense, this is logarithmic theories which are non-unitary.
Yeah, they are non-unitary. Mm-hmm.
So that's not usual. bridge what's the space.
Yes. Okay, so let me summarize and conclude. So I hoped that I could convince you that there are a huge number of new conformal field theories which have the supergroup symmetry, and that the supersymmetry implies very special features of the resulting CFTs. Namely, you always have an atypical sector which is manifestly non-chiral, so where the representations don't split into left times right. And this leads to the fact that you have a logarithmic conformal field theory. Then I showed you that a large class of supergroup Westominov-Witten models can be solved by using this, what I call free fermion resolution, so using this grading, this Z grading. And by doing that, I could reduce the model to the bosonic subgroup. I guess Volker will maybe shortly mention also different classes of supergroup Westominov-Witten models in his talk next week. And in general, one could expect that the geometric interpretation of these models leads to more insights into the structure of general logarithmic CFTs. And we had a few comments about that in our paper, but I won't talk about this. And some outlook and speculations. As I said, Volker will probably talk about type 2 supergroups a bit. Then one would also need to solve gauged Westominov-Witten theories and these other coset models in order to get a handle on ADS theories. It might be that the indecomposable structure at the end might even help to solve the model, although it looks pretty weird. That was a proposal by Reed and Zaleur. But if you remember that you have these infinite dimensional representations occurring just because you get the non-chirality, then it means that if you perturb the model, that all these states will move simultaneously. So you don't have these little small representations, which you would expect from a small chiral symmetry, but you can have small chiral symmetry but huge representations, just because you have these indecomposable ones. So then there are questions regarding the pure spinor approach, whether you also need to use this for the pure spinor approach, and one would like to apply it to disordered systems and percolation and such things. Okay, that's where I stop.
Okay, questions?
So the origin of logarithmic conformal field theory is really in the structure representations that it's in the decomposed. That just inherited by algebraic reasons. Which algebraic reasons it doesn't have to do with Westominov model itself, just the structure.
And one important point which I didn't really stress here is, and if you have a conformal field theory, then the operator product expansion has to close. And I was mentioning that if you have a projective representation and you tensor it with another projective representation or any other representation, you will get a projective representation again. So in particular, if you take the tensor product of some arbitrary projective representation mu and the dual representation mu star, and you assume that this is projective and this is also projective, then it turns out that here in principle you would expect the vacuum representation appearing because you tensor the representation with its dual. But since the vacuum is never projective because it's atypical, you always get the projective cover of the atypical representation of the vacuum here, plus other stuff. So you automatically get these representations if you include other ones. And the only way out, at least the only way out that is known to me, is if you consider, for instance, Westominov-Witten models in the very quantum regime at very small levels. Because then, as Volker and Hubert-Zaleur showed, then you can do some additional truncation and end up with just irreducible representations. But in general, as soon as you have any representation here which is projective, so typical, as soon as you have any typical representation, then you always have these things in your CFT because the operator product expansion has to close, and then you automatically get these projective covers in the atypical sector.
Okay. Just so I can see that I've got the main lesson. Because there's a distinction between irreducible and indecomposable for all, apart from one exception, that means that the Casimir is not diagonalizable, and it's that off diagonal piece that's giving you this.
Yeah.
Problem.
Yep.
You mentioned that there are at least some cases where there is a modulus that interpolates between the current algebra case without.
Yeah, I have one other transparency. So in this case, which is maybe physically also one of the interesting, where you consider AD as 3 times S3 with a flux which is not the pure Neville-Schwarz flux, you have such a modulus. And so in these models, you can choose the metric, the coefficient in front of the metric term independently from the coefficient in front of the topological term. So you have a marginal perturbation by the kinetic term, and that would lead to physical models which sit on these blue lines here. The blue lines are deformed Wess-Zumino-Witten models which geometrically describe a mixture of Neville-Schwarz and Ramond-Ramond flux. Or if you even forget about this Wess-Zumino term, then you can sit here on the green line, which corresponds to the principal chiral model, which is pure Ramond-Ramond flux. So these models have been discussed by Berkowitz, Waffer, and Witten, and Bershadsky, Weintraub, and Zhukov. And in principle, I mean, we are about to, or we are in the process of really discussing these perturbations and calculating conformal dimensions. But since that's work in progress, I didn't include it here. And
you can discuss those things for small perturbations around the.
No, you can do it to all orders in the perturbation parameter. At least that's what we believe.
You think you can say something about the principal chiral model itself?
That's a bit problematic because for the principal chiral model you cannot start with the Wess-Zumino-Witten model.
Yes.
But I would assume that the principal chiral model can be obtained as
I
lambda
would
to
as long as you
infinity.
go far enough up that
precisely.
line,
Yeah.
then
So in that sense, I would agree that you can also describe the principal chiral model in some limiting regime. Yeah.
More? Okay, let's thank Thomas again.